This is the video for section 3.4 on optimization problems, right? So to optimize means to make something as good as possible. And we know that very often when we're trying to make a decision, it boils down to one of two things. There's something that we want, and we want to make it as big as possible, and we want to know how to do that. Or there's something we don't want, and we want to make it as small as possible. So, maybe you want to do something in as little time as possible because, you don't want to spend a lot of time on something and you ask, how can I do this as quickly as possible? How can I minimize the time? Maybe in a business venture, you want to maximize your profit. So many things that people want to do boil down to I want something to be as big as possible or as small as possible. These are examples of what's called optimization. And it's an enormous part of how math is applied in decision making in science, engineering, certainly business. The way it's done there is very, very sophisticated, but we'll at least get some idea of how it works. So I'm going to illustrate all the steps with one example. So I'm doing one specific example, but you'll notice I have steps here that are abstract enough and general enough that you can follow the same steps for any problem. So here is our problem here. A cardboard box will have a square base, four rectangular sides, and an open top. Right, so let me draw this. Probably a picture would be included if I were asking you to do this on a test or quiz. So this is 3D, so I'm going to attempt to give you a sense of the 3D picture. Let me fix this a little bit, just change the perspective. Oh, sorry, I should have drawn the picture in advance. So here would be an example. We're going to have a box. It has a square base, but the height, we're not saying it's a cube. There is the back. And so the idea is this down here is the base. There are four sides, but this here is open, right? So I hope that you can visualize that. It's like, a brick shaped thing, but there's only cardboard on four sides so that we can put things into it on five sides, so we can put things into it on the top. There's a base and four sides, which makes for five faces. And what we want to do is we want to build this out of cardboard so that we're using only 108 square inches of cardboard. So even though we know that we have a square base, there are several different ways to do that, right? Maybe we want to do it where the base is kind of small and we get a very tall box. Maybe there's another way to do it where the base is quite big, but we have a short box. This description is general enough that it's not saying exactly what this box will look like. It's just saying, here's the requirement. The requirement is that it has a square base and an open top. We want to find the maximum possible volume for such a box. Is it a good idea to make it kind of narrow at the bottom and very tall? Is it a good idea to make it very wide but short? It's not obvious what's the best way to do this. So here's what we're going to do. Step one, we want to find some formula measuring the quantity we're trying to maximize or minimize. So we are trying to maximize volume of a rectangular prism. And volume of a rectangular prism would be length times width times height. So we can just start with that, length times width times height. That's how we measure this volume. And in some problems, if it's sophisticated enough, maybe you'll be given the key information, but often it's, volume of a box, area of a rectangle, um, things like that, where you should be able to figure it out pretty quickly. Okay, now what we're going to do is we're going to look at our formula and see if it has just one input variable. So right away, we're seeing to know volume, I need to know length and width and height. So in its current form, it has three input variables. we want to somehow say, can we use additional information in the problem to get it in terms of just one? So we want to reread the problem and see what do we know. So first of all, we know it has a square base. So because it has a square base, I could go back here and say, I didn't need to give these two different names. I could have called them both W, right? I'm going to call them both W for width. If you want to call them both X, just so it feels more mathy, more algebraic, that's great. Now, what about the height? We haven't yet used this number 108. We know that the total area used on those 5 faces should be 108, right? So let's write down what we know. We know that the total area of the 5 faces equals 108. So let's turn that into an equation. The bottom is W by W. So the area of that bottom squared is W squared. Now, on each side, we have a rectangle. And we have a rectangle whose area would be W plus H, W times H. And we do that for each one of these 4 sides. So what we really have here is that W squared plus 4 times WH equals 108. So what we can realize here is that there's actually a relationship between width and height. If I can't just pick them independently, they have to be related by this equation. So now what I can do is I can isolate one of the variables. And I notice H only occurs once, so that will probably be easier. I can say 4WH equals 108 minus W squared. So H equals 108 minus W squared over 4W. So I know that W and H are W and L are the same thing. And I know this is my relationship for H. So I could go back to this formula and say, hey, I can now write this just in terms of W. I can say that V is length, which is the same as W, times W, times height, which is this expression. If I know simply the width, I can figure out what is the corresponding length, what is the corresponding height, and what is the corresponding volume. And let's write what we have here as a function. We can think volume is a function of W. If I plug in W, I get volume. We'll notice that we have a little bit of cancellation here. So this is W times 108 minus W squared over 4, which is 108W over 4 minus W cubed over 4. And we could write that as, if we simplify this one, 27W minus W cubed over 4. So I'm going to put this in a dotted box. We're not done the problem, but we've done something really important along the way to the problem. So we now have a way of measuring volume in terms of just one input variable. And this problem is about volume. We're trying to maximize the volume. Okay, now let's reflect upon our input value and think what actually makes sense. As a mathematical expression, we could plug any value of W in here, but W represents the width of a box. So we're going to just notice, right? W can't be negative. It really doesn't make sense. In most word problems, negative numbers don't make sense. And if we wanted to know the biggest possible value, we could theoretically say, what if we made our height equal to 0? And it was just a square like that. Well, that square would eat up all 108. So W would be the square root of 108. So this problem only makes sense if W is between those two. And our formula is only relevant if W is in this range. But let's think about what are we trying to do in this problem? We are trying to find the maximum volume. So if we reflect upon this, this would basically mean make the width as small as possible, which means we'd have this ridiculous looking box. Or I'm going to draw a picture and delete it. But it would be like, oh, W is super duper microscopic, possibly even zero. And then we have this really, really tall box. If one dimension gets smaller, the others get bigger. This thing is super duper skinny. It's not going to have a lot of volume. Similarly, if we make width as big as possible, right, it would look something like so, or maybe we could imagine it's microscopically tall. So it is a box, but it's a box that really just looks like a square with a little bit of layering on it. Again, that's going to have really low volume because one of the dimensions is almost zero. So what's happening here and what happens in a lot of these word problems is theoretically there's this interval, but it doesn't even matter, right? One endpoint means make the width as small as possible. That is not going to give us a lot of volume. The other is saying make the width as big as possible. That also will not give us a lot of volume. So something we just want to file away is that these endpoints will not maximize volume. Okay, so now we go to step 4. We're going to remind ourselves that we have a nice function here and that an absolute extremum, the maximum or minimum we're trying to find in this problem, will occur only at an endpoint or critical value. So we'll find the endpoints of critical values and plug in. However, we already know that the endpoints won't give us the desired answer. And that is typical. In most of these problems, you realize that the endpoints are kind of silly. So what that means is in this example, the maximum volume must occur at a critical value. As a general principle, the maximum occurs at an endpoint or a critical value. For this example, making the width really, really small is a dumb idea. Making the width really, really big is a dumb idea. So now let's just find a critical value. So we will remind ourselves over here was our volume formula. So we'll recopy that. V of W equals 27W minus W cubed over 4. Critical value is where the derivative is 0 or undefined. Variable here is called W, but calculus is still the same. So 27 minus, let's remember that 4 on the bottom just means times 1/4. Right? If you want to write it this way, don't use the quotient rule when you don't need it. So we would have minus 3/4 W squared. So if we set this equal to 0, let's multiply everything by 4. Let's divide everything by 3. And so this factors. So we would have W equals 6, W equals -6. This problem only makes sense for positive values of W. So what we're noticing here is this is the only critical value relevant to the problem. So it gives us the maximum. So we know something really important, but we haven't necessarily answered the question. I'm going to type what we know so far. What we know so far, that if the width is set to 6 inches, then we will get the maximum possible area. Or not area, volume, sorry. The maximum occurs at a critical value. And we found what that critical value is. Right? So we have really key information so far. But now, what is step 5? Right? We have a lot of information. Let's reread the original problem to make sure that we're answering the question that was actually posed. So if I scroll up here, right, the question is, what is the maximum possible volume? So we have not answered that, right? The number we have is not a v equals some number. What we have is w equals some number. So what we can do here is we can say, okay, for our maximum, we want the width to be equal to 6. But what is that maximum volume? So we go looking at our work somewhere to see, do we already have a formula to plug into? Almost certainly you will. Read carefully, make sure you know what you're trying to find. Make sure you understand what you found so far. And so now we want to know, what is the maximum possible volume? So we can compute V of 6 based upon this formula here. V of 6 would be 27 times 6 minus 6 cubed over 4. Feel free to use a calculator. I don't have one handy with me as I do this, but this is going to be 162. This is going to be 216 over 4. 216 over 4 is 54. And so what I get here is this is 108, and it's a volume, so that would be cubic inches. That the number 108 occurred earlier in the problem as an area is a coincidence. So this is the maximum possible area. And if we want to plug back, if we want to actually make sense of this, we could go back here and say, okay, W is equal to 6, L is the same as W. H, our height, would be 108 minus 6 squared over 4 times 6, which is 108 minus 36 over 24, which is 72 over 24, which is 3. So it turns out the best possible arrangement for this box would be 6 inches on this side, 6 inches on this side, and 3 inches tall. So we're actually better off with a box that's kind of wide but short. That, it turns out, is going to be the best possible arrangement for such a box. So just to summarize, this procedure that we're seeing is like related rates. The details of each problem are different, right? Here's a problem about a box. The next problem might be about something else. And the exact calculus steps are different, but the overall strategy is the same. So when in doubt, just follow these steps. For any optimization problem, you will be able to do step 1 and step 2 and step 3 and step 4 and step 5. Follow the steps in a general way, but don't worry about trying to mimic specific calculations. And also, just section in the book, section 3.4 has other examples. Section 3.5 has even more examples related to economics and business. I think you're better off just doing the practice in class. So I'm not going to put more examples in this video. I'm not even going to make a video for 3.5, but we'll just do a lot of practice in the very near future. Okay, this video is already a little too long. I will end.